We'll go into the next module here, which is the in-place density test. The two tests that we're going to talk about here in this module is the sand cone test and the water balloon. Both really achieve the same thing. They determine what the in-place density is out on the project at any time during the compaction process. And they really should arrive at the same thing. It's just that it's a little different path for each one. The water balloon is the middle picture here, where I have my pointer here, and then the sand cone over to the right, upper right. The reason we're bringing the specifications in here now is because a lot of the things we've been talking about really are related to the specifications here. What we're really talking about here is with all these tests and what we're doing today is really what they call type A compaction. And there's actually a couple more types of compaction in the specifications. One is a B and a C, and they are mostly more like a method spec where you kind of tell the contractor maybe what to do, or more visual inspection compaction. If you're right now, the way our spec is, for instance, on some like maybe shoulder areas and say for a base, and base is really soil too. A type B or type compaction, for instance, is really how many, like a pneumatic roller is going over it to the point where it doesn't sink in anymore. That's basically what they call a visual compaction. Nothing's really measured there. In the case of type A, which we're talking about here, and that's what these tests are about, that we're actually measuring the compaction. And what we're going to be doing is we're going to, once we get out in the field, we've ran these tests. We've ran what they call the Proctor test that Mark went through. And this is what we're going to gear everything to when we get out there for that particular soil. We're actually going to gear everything to it. Everything is going to be relative to it, so to speak. So in this case, we have compaction control type A, and here's the two energies or the work that's put into it out there, or possible, that we have, T180, T99. We went over those. That's the work put into it in the lab. And in the case of, for instance, depending on the type of soil, this is what your particular, like for instance, your plans will specify which type of Proctor you're going to be using on the soil out there. So in the case of a T180, it says compact material to at least 90% of the maximum dry density with a moisture content no less than optimum moisture and no more than 5% each points above the moisture content. So what is that actually saying out there that we've heard? We've heard maximum dry density. We've heard that term already. We've heard optimum moisture. And that's basically what our result is when we do that Proctor test. So that curve that we created from those 5 points give us that maximum dry density, which is that crest, the crest of the curve. And immediately below that, at whatever the moisture content is at that crest, is really the optimum moisture. So we're talking about those things here. So when you get out in the field, yes, it would be great if the contractor could compact it to, say, that crest of that curve and right at that optimum moisture content. That would be just perfect. But reality is that, the Proctor is a lab test, and now we're out in the field, and there's lots of variables out in the field. So what we try to do is find an acceptable window for the contractor to work in. In the case of this, for T190, for instance, we'd like to get the material or have the contractor compact it to at least 90% of what the maximum dry density is. If the maximum dry density is 100 pounds per cubic foot, then we want to have them get it to at least 90 pounds, the dry density to at least 90 pounds per cubic foot. The moisture, that instead of just having it at optimum moisture, say it's at 10%, we're going to give them a range to work in from 10 to 15%. So as long as they're in those areas, in those two areas, at or above 90% or within that range of 5 percentage points, then that's okay. Then it's compacted to what we want. Now, T180 is basically what we would call, if your plans didn't say anything else, that's what your soil would be compacted to out there. If your plan note states that it's T99, As you can see from the first sentence up there, unless the contract specifies otherwise, if your plan note or your plans say it should be T99, then you compact it to T99. And so in this case, T99 is a little bit more stringent in the sense that we want at least 95% of maximum dry density. And the moisture content is a little bit wider too. It actually starts from your optimum. So if the optimum was, say, 15%, you would actually go 4 percentage points below that or 5 percentage points above. So the contractor can work in that range when they're out in the field. And I guess I just kind of went over this, that the T180 is actually the standard or what the spec book specifies unless the plans say otherwise. Basically, you have the same thing for pipe compaction too. 700 is where your centerline pipe compactions are, specifications, and if you're out in a centerline pipe project, you would be compacting it to a type A compaction, which is basically the same thing. The moisture range of the on a T180, and basically everything is T180 when you're getting out into the pipe material, because it's basically more of a granular soil, and that works better with the T180. But the range is a little bit different from soil that was in the 203. Remember back in 203, it was optimum to 5 percentage points above. We found it works better if the range, although it's still 5% range there, but it's actually set back a little bit from optimum, 2 percentage points, and then the range would be then 2 percentage points below optimum and 3 percentage points above optimum. So that's your range that the contractor works in. Still at 90% or above for the actual compaction part for the dry density. Do you want to start with a few procedures first?
Yeah, and just to note too, on the granular backfill for a T180, it's a 6-inch lift, but you only test every 12 inches. Kurt had that note on the other previous slide, but you want to make sure you put it in 6-inch lifts, but you only test every foot. So just a little note for you. Just a few highlights out of the procedure. I record the balloon readings to the nearest 100,000ths, or 5 decimal places. There is a chart in there for the minimum volume of the hole. For it to be a valid test in the state of North Dakota, it has to be a minimum of 0.25 cubic foot for the hole on your volume meter. You can dig the hole with an auger, trawl, or other tools, screwdriver. I've even seen attachments that people have used on your cordless drills to be able to dig down into the clay, but they need to be a 4 to 5 inch deep hole with a concave bottom. You weigh your soil removed to the nearest hundredth of a pound and record. Use a representative portion of the sample for your moisture determination, and then really for your speedy and microwave, you don't want to use any particles that will be retained on the number 4. And then you report your dry density to the nearest tenth of a cubic foot, or pounds per cubic foot. And then we'll watch the video, Kurt.
Okay.
Hi, I'm Mark Riley with the North Dakota DOT Fargo District. I'm going to show you the process of the North Dakota D2167 density and unit weight in place soil by the rubber balloon method. This method can be found in our field sampling and testing manual. If you're not sure your field sampling testing manual is updated, please check the North Dakota DOT website for the most updated copies. So, you will need a volume meter that has been calibrated. So inside the box here is my kit. We have our calibration form. Every piece of equipment should have one of these that's been done in the last year. Inside the kit, you can use them if you want. Needle pads, I strongly suggest them. Some sort of a hammer to get the pins in. Our volume meter. A spoon. The pins, the rubber balloon. Okay. You will also need a moisture tight container to put your sample in. And now that you have all your equipment, you need to determine the location of your sample. That is done by the random by getting a random number and by your lots for this length and of your material you're placing. So you get your random number, you got your location. You'll go out into the field, have a dozer or a blade, somebody cut you a spot, and you may need to take your square nose shovel and flatten out the spot. And you want your plate set flat and not rock. You take your pins, and you pound your pins down tight so your plate does not move. After your plate is down, you place your volume meter on. Most volume meters have marks on the volume meter plate, or I always set mine in the corner, which happens to be my volume meter. So then you would take your initial reading by pumping, inserting the bulb, opening the valve. You pump up to your initial pressure that was calibrated, which on mine is 2.0. So it would be a 0.01075 is my initial pressure. Close your valve, reverse your bulb, reopen your valve, pump the balloon until it just comes up. There is a standpipe in here, you don't want to pump that water above the standpipe, or you pump water back into your balloon, or into your bulb. So now that your initial pressure is done, take your spoon, and you dig out your hole, place the material from that hole into your moisture-proof bucket. You're then going to dig a 4-inch diameter hole, 4 to 5 inches deep with a concave bottom. And the minimum you need for the volume of the hole is a 0.025 for the volume of your hole to make it a standard test. So once all your material's out, place the lid back on your bucket so it can be weighed and figure out your calculations. Just to show you that I can get a higher reading for the final reading, I'm going to place it on this old cylinder mold here, or tractor mold. So now you place your back on your plate, open the valve, and pump back up to 2.0 on my volume here. And 0.02575 is my final reading. Now you take, reverse the bulb, reopen this, and repump up the balloon until it just comes back into the sight glass. You don't want to overpump this. Now you take material that you put in your bucket, you weigh it, put your initial pressure and your final pressure on the form, and you figure out your in-place density with your Proctor information that you got. That is the use of the DOT volume meter.
From there, we'll jump into the to the forms the form you actually use. I guess all through this class, there's only about three or four forms that we're going to use. So we had the first form where we talked about the Proctor and the worksheet involved. And so this is the one that really, this form here actually brings a lot of things together. We're going to actually enter what we get on the water balloon in-place density test on this form. We're also going to put some moisture information on here. And also, once we get our reading here, our in-place density, we're actually going to compare that reading. So in the case, we're going to actually determine what the dry density and what the moisture is of the soil that we're testing out there. And we're going to compare it to the Proctor that we'd made for this soil. And that's how the specifications tie into it. So when the contractor is out there and they're compacting this soil, and they're trying to get it to a point where, in the case of a T180, we want to have it at least 90% of what the Proctor is. And so we're going to determine all that by the test we take here. the first thing, and there's actually three things in order to make all this work. We have what Mark just demonstrated, which is the balloon method. And really, the balloon method, that particular apparatus there, it does one thing for us, and that it actually determines the volume of the hole that we're working with. We have to get a volume. And there's two other things that we need. We have to know what the weight of the soil is that we take out of that hole. And after that, we need to take a moisture of it. So those three things are going to help us get what we call dry density out in place in the road. And so the first thing, the first section up here, which is the test, this first section here is really just your location area. And basically the contractor is going to, they're going to be compacting the soil out there, and they're going to determine, well, I think I might have density here. So they're going to contact you, and they're going to say, if you're out there testing, and they're going to say, I want to test. And so the best, so the contractor is going to scrape away an area here, level area, so that you can set up your test area. And then you're going to run it. You're going to determine what the locations are, the stationing. It's all based on random numbers. You're in a certain lot size, and so from there, you set your test up on the flat piece of ground here, and you need a basis to go by. You need something to compare against. So what you do is you take that initial reading, right? Just basically right on that area right there without the hole being dug. You get your initial reading off this here. And as you can see from this gauge here on the volume vessel, is that it's got kind of a meniscus. It's kind of like a glass of water. It has a meniscus to it. So you want to make sure you read either the bottom or the top of that meniscus, just so you do the same every time for the initial final reading. So you get your reading directly off of here, and you put it here. The next step is to dig your hole. As Mark said, put the material in the container and weigh it. And here you have the weight of the soil. You put this in line D. After you do that, you put back your volume vessel, and you get a second reading, which is it's going to be the one that when the hole is dug. So, and really what's happening here, as you can see this schematic here, is that once as Mark pushes air into it, it actually drives down a balloon, liquid-filled balloon into the hole. It actually molds the hole that you did. So it's actually, so the final reading minus the initial reading is going to give you the volume of the test hole, which is what's in green here. So now you have a volume and you have a weight. What you can get out of that then, those two things, as we kind of did, back when we did the Proctor, is that you can get a wet density. Weight over volume. Wet density is basically the density of the soil in wet soil. And what we want to determine here is F, which is the dry density. And before we do that, we have to take the material after it's been weighed and do a moisture on it. And so the first thing we're going to do, as we did earlier with the Proctor, is we get the wet weight, get a dry weight, and then once it's dry, then we know what our moisture loss is. Next step in moistures is to determine, once you have your dry weight, if you subtract that from the tare weight of the container, now you have the dry weight of the soil. So moisture, once again, is moisture loss divided by the dry weight of the soil, which gives you the moisture content. Now you need that moisture content up in line F. You put that up there again, because you're going to need it for the calculation of the dry density. And that's what we're looking for. Our Proctor was done in dry densities. So we need the soil out here being reported in a dry density. And we got our wet density. We have our moisture, so we can determine from this calculation what the dry density is. It's basically wet density times 100 divided by 100 plus whatever the moisture is. So in this case, it would be 100 plus 11.9. So you'd actually divide this by 111.9 into the numerator there. And that would come up with a lesser number density of 13.2. So that's We need this number, and we've got this number. Now, the next step is, okay, does it meet specifications? Does it, this is a T180 that we're doing here. So does it actually meet the T180 proctor for this particular soil? And so this is kind of a busy slide, but we have our specifications. If you remember, for a T180 is the soil out there has to be compacted to at least 90% of the maximum dry density, and it can be in a moisture range from the optimum 5% above. So in this case, we'll just go down to this section here to start with. This is where we put our proctor information. Well, I guess this one here, excuse me, the third section here. So we'll bring the proctor in from, and this is a different one from the one we did earlier, but this is the actual one we used here. So we had a 124 was the actual maximum dry density, and the optimum moisture was 10.2. So we have that information, and and whatever we did on the soil sample out there, on the soil, was our dry density was 113.2. So what we want to do is we want to divide this 113.2 by our proctor number, 124, and that'll give us a percentage of compaction. And in this case, if we go down here to line L, that's what was done. And so it's a percentage of maximum dry density done. So in this case, when we did that calculation, we got 91.3. So in this case, our required was 90, as the specification mentioned. And so it actually passes the compaction, but we're not through yet. We have to determine if that percent compaction was done in the moisture range that we wanted it to be in. And if you remember from our specifications, for a T180, the moisture range that we could work in out there is from optimum to 5% points above. So there's your moisture range. Remember our proctor's 10.2, so we're going from 10.2 to 15.2. We can work in that range. Our moisture content that we actually, from the actual soil that was there, was 11.9. So you can see that in this case, both things passed, and they both have to pass in this case for the contractor to continue on and to put another lift on. Basically, this form here kind of puts everything together when you're out there. It kind of brings in, ties the proctor to it and the moisture and everything. Any comments on that, Mark?
Both the moisture and the dry density have to be met for a passing sample. I think some people think that if it meets the maximum dry density and it's outside the moisture, it's still a passing sample, but it is not. It has to meet both criteria.
Right, exactly. Go ahead, Mark, if you want to.
Okay, and then this just shows up here on the top is that proctor that Kurt used on the previous form, and then our compaction point of 91.3% to 113. Here's the green. You notice that we are quite a few curves below the proctor curve, but we did pass our compaction. But you might want to start considering that if you're consistently running down here and it's really, really hard, like it was on your maximum dry density for pounding your proctor, if that material is like that hard, you might want to consider that your material has changed. You may need to start thinking about running a new proctor. It is passing, but if it keeps changing or keeps staying in this consistent area, you might want to consider running a new proctor. And then I'll always encourage you to plot your proctor information on there and then plot your compaction points on to make sure that it looks right. Am I using the right proctor? So you'd have one proctor here and say your next proctor was right here, just above this green. So you should actually have been using that proctor. So it's just the way if you plot all your proctors on the family of curves and then plot your compaction points on there, it's a way of telling to make sure you're using the right proctor. And then if your point comes out near that 100% saturation line or on the right side of it and you're getting a passing sample, you obviously have something wrong because all your voids are filled with water and not the air wasn't drawn out and filled with moisture or dirt. So you want to make sure that if you're out here, you have a problem. It's either math or procedure, you miscalculated a number or wrote a number down wrong. So at which point you might want to rerun your test.
Okay, I think we'll go right into the other way to do an in-place density. And Mark, if you want to go ahead, go with some procedures to start with.
Okay, the next in-place density is sand cone method. I just want to touch on a few things. Filling the apparatus, make sure it's upright on a level, firm surface. You want to close the valve and fill the funnel with sand. Once the funnel's full of sand, you can open the valve and keep the funnel at least half full of sand while filling. And when the sand overflows, stops flowing into the container and over the top of the cone, then you can close the valve and get rid of the excess material out of the cone. For each container or bag of sand, there's a unique cone correction and sand calibration factor. Each cone base plate will have its own cone correction and bulk sand densities. And like I said, you make sure you change sources or different lot numbers in your sand. Make sure you redo your cone correction and calibration for those. Any vibration during the sand cone method may increase the bulk density of the sand and decrease the accuracy of the field test. Select your area. The base plate stays in place. You put your base plate down and then you can start digging your hole. The plate stays in position for that. And make sure your hole's 4 to 5 inches deep, 6 inches in diameter. The DOT only allows the 6-inch sand cone. I know some of the testing firms have a 4-inch, but we only allow the 6-inch. Again, in the procedure, there is a minimum hole for the volume of the hole for the size particles. Again, weigh to the nearest 100th of a pound and record your weight to the nearest hole number, and then a 1/10 of a percent for your moisture. That's it.
Okay.
Procedures.
A little bit of a procedure for starting filling up your container before you do the sand cone test. So here it is. Basically a matter of filling it up pretty much full, and once you do that, then you can turn your valve on.
Yeah, so we fill it up all the way, let it drain down a little ways.
Okay, we'll watch the actual sand cone video once we've filled it. Now Mark will go into the process of doing some other things, including some of the calibration stuff before we start. So here we go.
Hi, I'm Mark Greta with the North Dakota DOT Fargo District. I'm going to show you the North Dakota T191 density of soil in place by sand cone out of the North Dakota DOT Field Sampling and Testing Manual. If you're not sure yours is updated, please check the North Dakota DOT website for the most current version. Okay, so in our sand cone kit, it's our calibration form. It must be updated every 12 months yearly. And our sand cone. Sand cone base. Again, a Neopad. pins to hold on our plate, spoons, screwdriver, depending on what type of soil, to get the soil loosened up. Brush to sweep the fines back into the hole so you can get them into your moisture-proof bucket, and a hammer to get your pins driven. Okay, before we can go out in the field to do our sand cone, we need to have our cone correction. To do the cone correction, I'm going to place a plate underneath my steel plate, so now all I have is the bottom of this plate and my cone, which is my cone correction. So I start with a known weight, set my cone on my plate, line up the marks, then you would open the valve and watch or listen for the sand to quit moving. And it's important that there's no vibrations going on while this is going down, so we don't compact any of the material in this cone. So once your sand would stop, you'd shut the valve, pull the sand cone off, and you would weigh the sand cone again, and the weight between the full and what you have left on the form is your cone correction. Okay, so now we have our cone correction. We also need the unit weight of our sand. Here in the Fargo District, I use a 1/10 cubic foot pot. Place my plate on top of the pot. We start out with my known weight full sand cone. Place it on top. Line your marks up. Open the valve. Watch and listen for the sand to stop going. Make sure there's no vibrations again. Once that's done, close your valve, take it off, weigh your cone again, and then you would have your 1/10 of your cubic foot, so then we can times our number by 10 to get the density of our sand. So now we got our unit weight of our sand and our cone correction. We can go out into the field and get our location by just the random numbers. Again, you'd have a dozer or a blade cut you a spot, level it out with your square nose shovel so your plate doesn't rock. Take your pins, your hammer, drive your pins in until your plate is flat and does not move. Now, depending on what type of material you're using, you can use an auger, spoon, screwdriver, and hammer. Get down. You want to dig this material out of the hole, 6 inches in diameter, 4 to 5 inches deep. Get all the material out of the hole. Take your brush the material back into the hole. Get all that material out. You know, 4 to 5 inch deep hole with a concave bottom. Once it's all back in your moisture tank container, cover it. Safe to weigh at the end. Now you take your already known weight full sand cone, put it on your plate, line your marks up, open your valve, make sure that before you open your valve, make sure there's equipment stopped running, no vibrations around the sand cone. Then you would open your valve, watch and listen for the sand to quit moving. Shut your valve, pull your sand cone up, reweigh this. So you have an initial weight, the final weight. You have your weight of the material taken out of the hole, put on your form. You calculate with your proctor material or your proctor that you already have. Thank you.
And you may have mentioned this, I didn't, you probably did, but when you're out on a project, it's good to shut everything down and so there isn't very much vibration when you actually do the test, because the vibration of the equipment around it can cause it to densify more in the hole. The sand, you want to be able to have a free, the sand once it flows in, you don't want anything affecting it. With that, I think we will go into once again to the worksheets here. The worksheet that you actually use before we go out to take the test, as Mark was mentioning, is that you got to do a couple of things beforehand. And one of them is you have to determine how much material does this cone actually hold, because that has to be taken out of the calculation. As you can see from the bottom photo down here, if there was a test hole in there below this, it wouldn't, it doesn't really tell us anything. Is once we've ran the test, if we have this cone material that filled the cone in there, we have to try to subtract that out of the equation so that all you have is the test hole. And so basically that's what this first half of this form does, is that you actually do 3 readings where you have an initial reading and a final reading. And what you're trying to figure out here is what your how much weight the cone is got involved in it. So in this case, the cone correction factor after 3 tries, and they have to be really close, pretty close. And then so in this case, the cone actually, the weight of the sand that filled the cone here was 3.57 pounds. And so we need that as we do our calculations out in the field. Now the bottom half of this form here is basically what's the density of the sand that we're using for the test. This is kind of like a pool sand. I don't know if you've been around swimming pools or anything. I think it's more of a filter sand. So what you do is just as Mark had there, you fill the sand, fill a known volume out there of what it is with a known volume container. And, there it is, there's density. What we're looking for is density in this case. And so you have your, whatever the weight of the sand is that filled that known volume, you can figure out what the density is. And that's done actually 2 or 3 times. I guess I go to the next slide and show how that procedure is done too. In this case, the sand actually weighs 95 pounds per cubic foot. That's something we have to have before we go into the form there where we're doing the in-place density. We have to know what the sand density is. And so proceeding forward, we have these 2 numbers now, and we can go into when we're out to do the test. Once again, the contractor is going to ask for a test. So we randomly select an area, clear out an area, and take a test. Now this could be on a grading project, or it could be on a soil compaction or a pipe compaction project. And so we know an initial weight of the soil, and we have another unit weight here. We have 95 pounds per cubic foot. We want to know that. So we're going to, once we go out there, we're going to put our plate down. We're going to immediately, we don't need an initial reading here, so to speak, like we do the water balloon. We just go out and we dig the hole first and put it in a container, airtight container, and weigh it. And this is our soil weight. And then we continue on. Once we got our hole dug and we got the soil out, then we can actually take the apparatus again. Apparatus that's been pre-weighed, which is our initial weight here, and then we let the material flow down through into the test hole, and it's also going to fill up this cone. And once we're done with that, then we weigh this, and this is what I call our final weight. So that weight of that sand includes what's in the test hole and this cone. So the idea now is we want to get rid of that cone, whatever is in that cone. So all we have is what the sand that's in that test hole. Here's our situation where we've got the weight of the sand in the funnel and the hole. So we know that from the initial and final readings. And then from there, we can take from our previous form, our cone correction factor, and subtract that from it. So this is the weight of the sand that's in the cone. Subtract it, and then all this is basically the weight of sand in the hole, and that's what we're looking for. And so from there, now this is a little bit different from the water balloon in a sense that, okay, we know the weight of the sand in the hole is 4.816, but we also know that the unit weight of sand is 95 pounds per cubic foot. So if we divide that 95 into the 4.816, we'll get a density or a volume of the test hole. If this fills a cubic foot, 95 pounds, then this material here is going to fill only a certain amount of that cubic foot. In this case, only this much. So 0.0507 cubic feet is the volume. And that's basically just dividing the weight of the sand in the hole by the density of the sand, and that'll give you a volume. So now we have a volume. A little more calculation than the water balloon, but we finally get to a volume. So we have the volume of the test hole. The next thing we want to do is we have the weight of the soil, the weight of the wet soil that we took out of dug it out of the test hole. So we have that there. We have a volume now. So now weight over volume is wet density. It's the weight of the wet soil divided by the volume of the test hole. That'll give you the wet density, in this case 127.0. So we have that. Now, in order to do the dry density, once again, we have to go down and do the moistures. Kind of go through that same process that we did for the Proctor and for the water balloon method in order to determine what our actual moisture is. So here we have a moisture, 9.5. We know our wet density, so now we can go ahead and determine what our dry density is, which, once again, here's that calculation. Wet density times 100 divided by 100 plus the moisture content. In this case, it'd be 109. Your denominator here would be 109.5. That's what you'd be dividing into the wet density times 100. That'll give you a dry density. So here we are again. We're reduced it all down to a dry density. And now what we're going to do is we're going to compare it, just like we did for the water balloon method. We're going to compare it to the Proctor information. So in this case, we have for this particular Proctor, the soil that we did it on was a maximum dry density of 126 and optimum moisture 10.5. In this case, now that for this particular project that we're on here, this was actually a pipe project that we did this on. So remember from the specifications in the 700 section is that the T180, it's a little bit different as far as the moisture range when you're working with coarse grained soils like class 5s and things versus a fine grained soil. So the actual moisture range stays the same, but it's actually 2 back and 3 ahead of the optimum moisture of 10.5. So here we have our optimum moisture 10.5, which is the Proctor information, the maximum dry density 126. So in order to determine, we need a 90% minimum compaction, which is what we have here. That's what we have to meet. And so in order to determine if we have that, we want to divide the maximum dry density of 126, and we divide that into 116 dry density. That's the point we had out in the field. And the result of that is 92.1. So in this case, it actually met the compaction, but did it meet the moisture range? Our moisture of the actual soil that's out there that we took out of the test hole is 9.5. Our moisture range is 8.5 to 13.5. So yes, it did. And once again, as Mark mentioned earlier, both these things have to meet. It has to meet the moisture range. It has to meet the compaction in order for the contractor to put another lift on or continue forward. And the next slide here is basically talking about what Mark mentioned earlier, and if the thing you want to add to this, Mark.
Essentially, same thing. Make sure you plot your Proctors on there, plot your compaction points on to make sure you're picking the right Proctor. make sure you're not out to the 100% saturation line or beyond. So, so you can check your numbers, just basically use it as a tool to make sure that you're getting the best fit.